Hello and welcome to this video where we will be making a Tetris game in what is essentially C but technically C++. So Tetris of course looks like this, and we're going to try to create a complete game. So by complete game, what I mean is that we want to have a starting level selection, we want level progression, we want scores, we want a game over screen, we want to be able to start a new game, and so forth. So in order to do this, we need to get started, we need to work pretty fast. So I'm just going to go ahead and start writing the code, and I'll describe what we're doing along the way. So first of all, in order to properly be able to implement all the different phases of the game, we need to have split the update and rendering methods into different subsections so that we can, in a convenient manner, implement the different behaviors of the game in the different states. So, however, it's good to focus on the most important part, which is the part we actually play the game. So I'm going to start by assuming that we have some function called update game play, and then we have some function called update game, and this function will say we have some game state here. It's going to switch on this on the, let's call it phase, on the phase of the game, and it's going to run different functions depending on what phase we're in. Okay, so we'll start with the actual gameplay. So let's assume we have some game state structure. Then we want to represent the board here as an array of 8-bit values, where 0 is an empty cell and the other values represent different colors. So functionally, the game really only cares about whether a cell is empty or not, but for the presentation purposes in the rendering, we want to display different colors for the different values so that different Tetrinos have different colors. And what we're going to do is, if we look at the Tetris description here, the playing dimension should be 10 by 20. So the width here is 10, and the height we're going to put at 22, because we are going to have 2 hidden rows that we'll use to spawn new pieces so that they don't just pop into view. And then we're going to have what we'll call the visible height, and we'll set that to 20. So this board is going to be width times height. So we are projecting this two-dimensional matrix onto this one-dimensional array using the following indexing scheme. Values, we need to know the width, and we have the, actually, let's do it like this. We have the row and the column. Let's call it board get. We'll do, actually, take it back. Let's do it like this. Let's do a pure function here. We have the index, which will be row times width. Whoops. Index. So this gets value from the board at that coordinate, and we'll do a matrix set function as well, which does the same thing, except we want to set the value instead of returning it. Oh, my daughter is pulling the cord here. Okay, so here we set the value. Okay, so this is how we represent the playing field in the game. Uh, Next, we have the piece, the moving piece. So let's create a data structure for that, because we want to separate this from the board. Because the board is it's not static, but it contains the pieces that have been fixated, and the piece represents the moving part. So each piece, we'd first like to know which tetrino it is. So tetrinos are these different shapes. So let's put an index there to determine which one it is. And then we need to know where the piece currently is in the playing field. So we have an offset row and offset column. Next, we have a rotation, because they can be rotated. Okay, so let's put the piece into the game state. Now, what we're going to do with the tetrinos is that we have these indices, and we're going to create a structure called tetrino, which will represent these shapes. And here we expect to have some data. Let's call it a data. And this is a matrix, the same manner as what we did with the board, but it's a small one which represents the shape. And alongside that, we want to have a value representing the dimensions of this data. And here we're going to assume that this is a square matrix. So we have one side, and then that's enough. Let's go ahead and create a constructor function for that. There we go. Then the idea is for us to create a list of tetrinos, which this index refers to. So this index is into this array, and we'll define the various tetrinos. I'm going to do one of them now just to demonstrate what it is we're trying to achieve. So let's assume that the first one is going to be the bar. So you see the bar there, and it's a 4x4 matrix. So we define the first entry in the index with this as the data, and the side is 4. Let's do one more just to demonstrate this. We'll do this one, simplest one. Side is 2, and let's also do a third one. Let's do this one, the T-shaped one. There we go, and that one's gonna go in here. 3. Let's see if we can build. Oh yeah, we haven't defined phase yet. Enum game phase play was the one we used, right? So let's assume there is a phase in the game state. All right, so now we have our 3 tetrinos here. there are a total of 4 Tetrinos, but we'll go back and add the other ones later. So in order to be able to focus on the gameplay for now. So these mini matrices, we want to access them in the same way we did with the board here. But however, there's also a rotation, and the way I'm going to do the rotation is that I'm going to change how the indexing works in order to represent a rotation. So let me just demonstrate that real quick. So if we have a 3x3 matrix, and we can use this T-shape as the example. In the original orientation of the matrix, columns are in this direction, rows are in this direction. Now if we rotate this 45 degrees clockwise, we'll end up with a matrix that looks like this. Now the original columns go like this and the rows are up here. Okay, so we now have a different coordinate system which refers for this rotated shape where the rows are here and the columns are up here. And we see here that the row, the actual row into the actual matrix data is the reverse is the column of the rotated matrix in the reverse direction. So we have side minus C prime minus 1, and the column is just the row when accessing the rotated matrix. So if we try to do let's call it Tetrino get. If we get one of these Tetrinos in and we try to access a row and a column given a rotation, then if there is no rotation, we just do the same thing as above here. So we just return Tetrino data row times side plus column. If we have rotated 45 degrees, the row is actually this value. So we return Tetrino data. We do side minus the column that we're accessing minus 1. And the column is just a row. Now if we rotate this once more, we get the following matrix. Now C is over here, and now R is over there, and now the alternative coordinate system, C prime and R prime, looks like this. So now we see that the row is actually in the reverse direction of the R prime value, side minus R prime minus 1. And our column is the reverse of the column of the local of the other coordinate system. So it looks like this. basically, I hope this makes sense. I mean, in order to access elements in the actual matrix data, we need to know the row and column indices. Now when the thing is rotated, what we're actually referring to with the row and column values, the C and R prime. C and R prime are the row and column values we receive here. We are actually referring to this coordinate system, so we need to determine what the cell referred to by R prime and C prime actually refers to in terms of R and C. So this is the conversion. So this is what the conversion between projection between the two coordinate systems looks like. So in this case, we had Tetrino data. We had the row was side minus row minus 1. And the column was side minus column minus 1. And then the third case, we rotate this once more. So now the column is over here, and the row is over there. This is R prime, this is C prime. The thing looks like this. And we see that R is C prime, and C is R side minus R prime minus 1. So Tetrino data, this is just a column. And this is actually an error case, but we're just gonna return 0. Because we expect rotation to be either 0, 1, or 2 or 3, because we only have 4 different rotation states. Okay, so this allows us to get the value of the Tetrino with the rotation. Okay, very good. So now that we've done some, basically determined how we're going to represent the data here, let's come and actually start doing some gameplay code. So one of the things we want to do is we want to control this piece. So we need some inputs. So let's assume that there is an input state structure. Let's pass that in here. Const input state. Input goes in here. All right. Let's compile. Yeah, I need to define that. Struct input state. And okay, so basically you can move this piece to the left, to the right, you can rotate it, and you can make it drop faster. But let's start with the basic movements: left, right, and rotation. So if you try to move this piece out of bounds, or if there are lots of blocks here and you try to move into those blocks, we want to disallow that move. Also, if you rotate the piece so that its new orientation is such that it overlaps with something that's already on the screen, we want to disallow that as well. Now, in a more advanced version, you could do some kind of wall kick thing where if you rotate and it overlaps with something, you push the piece out so that it sort of like pushes itself away off of the wall. But we're going to start simple and just disallow the move if it results in an invalid state. So the way I'm going to implement this is that I'm actually going to create a copy of the piece in the game state. Then I'm going to change this piece. I'm going to validate that the new configuration of the piece is a valid state, and if it is, I'm going to update the piece in the game state by just copying the modified piece into that. If not, I'm just gonna not do anything. We just throw away this copy. So it's a very convenient way of implementing this. So we're gonna check the input state, and we're gonna say if d left is greater than 0, means so this is just a convention I usually use. So we'll define this input state structure soon, but let's assume that there is a field called dLeft, which signifies whether the left button, and left here is not necessarily a specific key on a keyboard or a gamepad. It's left it's left semantically from the perspective of the game. So whether that key has changed state into being pressed. That's basically what this means. So we'll probably have a field called left, which indicates whether the key is currently being pressed or not, and dLeft indicates whether the key changed its state into being pressed or being released. So if left was pressed, we will take this copy and we'll decrease the offset call. If right was pressed, we'll increase the offset column. If up was pressed, we'll rotate the piece and we'll just map it back onto this range. Next, we want to have a function which checks piece is valid. Let's call it like that. Check piece valid. Okay. And in order to do that, we need the board. We need probably the width and the height of the thing, and we're going to pass the piece in. So let's go ahead and implement that function, check piece valid. We'll take the board, the width, the height, and a piece state. Actually, let's pass this one first, because the naming of the function makes it. This can be const as well. I usually put const in, it's just a habit. Some people will probably argue with good arguments why it's completely unnecessary, since it's not since you can overrule it anyway, but I just do it out of habit. So we move this one in there, send the piece in, and the board, and the configuration of the board. Okay, so what are we trying to do? The piece has a Tetrino index, so we need to fetch the Tetrino first. So we go into the Tetrinos table and we fetch the Tetrino. Okay. Let's do an assert here. Oh, sorry. And then we want to loop through all of the cells that represent the Tetrino, and we want to check if any of those which are non-empty are either out of bounds or collide with anything on the board. So let's loop through all of the cells, and then we're gonna fetch the value Tetrino git. We're going to pass the Tetrino in, row, and column. Now, if the value is greater than 0, we need to project these row and columns to the coordinate system of the board. And so these are in the local coordinate system of the piece. The piece then obviously has the where is it? The offset row and column, which are in the coordinate system of the board. So we can find the board row as the piece offset row plus the local row. Board column equals piece offset column plus column. Now if this is less than 0, so this function obviously needs to return a value. So if it's less than 0, it's not valid. If it's greater than or equal to the height, it's not valid. If the column less than 0, it's not valid. If it's greater than or equal to the width, we are out of bounds, so it's not valid. And then finally, if the board has a value in this cell, which would mean that this function returns a value greater than 0. If there's a value in that board, we're not valid because we're going to collide with that cell. So this is basically collision detection on a grid. If we get through all of this and nothing fails, then we are good. It does not take 3. What does it take? Oh yeah, rotation. Cannot. Oh yeah. Tetrino get. This needs to be const, obviously. And we need to enter those variables. D right, D up. All right. So we have our check. So if it's valid, then we copy the modified piece into the game state. So we update the state of the piece in the game, and we're good. So I usually like to wait and do the front end stuff late, but let's actually do that now so that we can test some of this stuff. So I'm going to be using SDL for rendering and stuff like that as our platform layer. And that's because basically I want to focus on gameplay in this video. It would be too long if we're going to do rendering and all that stuff using Win32 or using OpenGL. So we're just going to keep it simple. We're going to use SDL. So we need to create a window. And we want to create a renderer. I'll initialize these. Later we'll also use SDLTTF to do some text rendering, but let's start with this. So let's initialize the thing. We want video. Let's see if I remember this correctly. If it's less than 0, it's a fail, I think. And then we're going to create this window. SDL create window. Let's just call it Tetris. Um, we'll do a window. It's easier to debug. I think window pos undefined. Is that the one? Let me check this. Yeah, we just get some random window position and size of the window. Let's do something like this. And we want OpenGL, and we want window shown, and we want a renderer. On this window. Let's look at that. Create SDL, create render. Index flags. Okay, index. All right, -1, and we want accelerated, and we want vsync. And then we need to do the cleanup. You don't actually need to do the cleanup, but I'm just going to do that anyway. And we're going to quit. Did I do that right or not? What's that one saying? Oh yeah, comma missing. Oh yeah. We need to use WinMain. So let's see if this runs. Yeah, we need SDL. Let me check this. That's the path. Let's see if this runs. Okay, we had the window pop up there for a very quick second, so let's do our loop. Let's also go ahead and do this. It's probably like that. Where did our window go? Oh yeah, sorry. Obviously this one needs to go here. There we go. Okay, we got our window here. Very nice. Okay, so let's do a. So that's the updating thing. Let's also do a void render game. We'll pass in the STL renderer. So game state should be const when we render it. Probably we'll see. Maybe we don't want to do that. Let's also create a game state instance on the stack. Let's do input state. I'm just going to keep things simple here and put them on the stack because they are pretty small, so we're not going to have an issue doing that. I'm going to do update game, and we'll do render game. Yeah, render. Then obviously we need to present what we rendered. So SDL present render present, is that the name? Renderer, there we go. So maybe we want a background color. Yeah, let's do that. Okay, let's see. Okay, great. Now, I'm actually gonna pull in a file I prepared previously, which looks like this, where I didn't want to type out all of these colors, so I looked up a set of colors I think are going to look nice. So I've prepared some structures for these colors, and we have a color struct and a constructor function, and we have a bunch of predefined colors for the different tetrinos. So the idea is that we just index into these arrays. So first tetrino, second, and so forth. So let's see if we can draw. Let's see, what do we want to do? We want to draw a cell. Basically, we want to draw the piece, but in order to do this, we need to first determine the grid size. So let's say grid size 30. Then we can do draw cell. Renderer. We get the renderer, and we need some coordinates for the thing. Row and column. We can do an SDL rect. Let's see. Is that the name of the thing? Yeah. SDL. Let's see. Yeah. That's the one. Okay, so basically we want to do draw cell. Let's do we have the row, we have the column, we have the color value, and then we want the offset on the screen of the thing. So yeah, then we're gonna do fill rect. So let's do fill rectangle. yeah, let's do it like this. Let's do fill rectangle where we have the x coordinate, the y coordinate, the width and the height, and the color using a color structure. We'll do the STL code here. STL rect x y height. Then we set render draw color. Such a long name. We pass in the various properties RGBA, and then we do render fill rect render and rect. So here we just need to map the grid coordinates onto screen coordinates using our grid size that we defined earlier. So essentially we have the x and the y, the width is grid size, and the color, we're going to fetch that from those, so you know, these ones, from these ones here. So we have the base color, we have the light color, and we have the dark color. And we're just gonna, you know, we're gonna do a lot of overdraws here, but just to get a nice effect. So we're gonna do the dark color first, filling the entire thing. Then we're gonna overdraw with smaller rectangles on top of that, so that we get the dark color in one of the edges and then the light color in the other edge. So yeah, render. So let's just pass this in. Let's do let's define the edge width as, let's say, 1/8 of the grid size. So we do x plus edge grid size minus the edge, obviously, and then the grid size minus the edge with the light color, x, y with height color, and then let's do x plus edge, y plus edge. Yeah, so we put the base color inside, so it has a margin on both sides, so that the dark color is on one corner and the light color in the other corner. So that's how we're going to draw a cell. Let's see, what did I miss? Oh yeah, let's do this. Let's copy this. Okay. Identify x. Oh yeah, we didn't compute the x. There we go. So that was a lot of mundane typing, but now at least we can we can draw something. So what we're going to do is we are going to render our piece. So let's create a draw piece function. We'll pass in the renderer again, and then we want a piece state, and we want to get this offset in because it's going to allow us to position the whole thing on the screen later on. Okay, so we have to loop through the yeah, we need the Tetrino, obviously. The Tetrino. Tetrinos plus piece Tetrino index. We loop through the sides of the Tetrino. Loop through all of the cells. And we need to fetch the value. Pass the Tetrino, the row, the column, and the piece rotation. And if the value is non-zero, we're going to draw a cell. And we're going to draw it at row plus piece offset row, because that's the world coordinate system. Value, and then just pass in the offset x and the offset y. Was that correct? It was. Very good. So here, let's just draw the piece. Let's just draw it in the upper left corner for now. And let's run this and see if it works. There we go. We have a piece, and it's being drawn, and you can see this little rendering detail we did, where we have the base color there, and then we have the borders. Okay, it's looking good. So we've got our piece there. Now we need to get some input state in so that we can move it around. Okay, so let's look at doing that. So we're going to use SDL for input, obviously, and then we can fill in the properties of the input state object appropriately. Okay, so let's do it here. We're gonna call SDL get keyboard state. Let's look at that just to make sure we do this right. Get keyboard state. Okay, so it returns a number of keys, and it returns an array with unsigned int values, 8-bit values, which tell you whether the key is pressed or not. Okay, so we have key count. We give it the pointer to that, and we expect to receive key states. It's good. Then we need to check whether scan code left. Actually, let's do this. Let's go ahead and let's go to input state. Let's introduce a variable or member called left. which will have the same type as this key state thing. So we'll say input left is equal to this. That should be valid, right? Yes. Then we have right and we have up. So right is and input up is simple. And then in order to do that delta d left, d right, d up thing, we will create variables here. Previous left value is what we had in this one here. Let's actually do it like this. Let's just copy that structure. And then here we just say d left is so it's just a change in that member. What's the problem? Let's see. Oh yeah, sorry. Input state is the name of the type. There we go. Let's see if this works. If we run the thing. Let's go down here. Let's look at this. Yeah, we can't debug that. Okay, we can move, but we can't move very far, so something is wrong. Let's look at this. Tetrino get. Did we do the rotations right? So why are we colliding on the right here? Let's see if we can debug this. It says that we're on the 10th column. Piece offset is 3. Column is 7. Oh, yeah. Okay, that was a stupid mistake. Obviously, we are not doing this. We are doing this. There we go. Let's try it now. Okay, it works very well. We reach the end of the board and we stop. And you see if we rotate, we can go a bit further. So our collision code is working as expected. So let's also try a different Tetrino shape. So let's do game.piece.tetrino index. Let's try the T shape. Yep. So we have the bounce checking working, and you can see the rotation is working as well. All right. So now that we have that part going, let's also see if we can draw the board. Because what we're going to do next is that we're going to merge the piece onto the board. And it's good if we can get visual feedback on whether that's working correctly or not. So that's obviously always a plus. So draw board. So it's very similar to the other one. We have the board, we have the width and the height. Let's put those on the same line. And we have the offset X, offset Y. We're just gonna loop through all of the cells. Like so. We're going to get the value using the matrix get function. Have the width, we have the row and the column. It's going to return us the value if the value is non-zero, so that it's not an empty thing. We're going to draw the cell, and we have the draw cell function there. Pass the renderer, we pass the row, the column, the value, offset X, offset Y, and this time they are in world coordinates. We don't need to do anything else, and we're done. So let's go down here. Render game. Let's draw the board. Game board width, height, and offset is 0. Run the game. All right, there's nothing on the board, so okay. Next up, we are going to do some more game programming. So let's go to the update game function. So now this part is working. The next thing we want to do is that we want to soft drop the piece when a certain time has passed. So let's see how that works. Basically, we take the piece, we move it down, and if it collides with the board, we move it back up one step, and then we fixate it there by copying the contents of the local matrix here onto the board, and then we spawn a new piece. All right, so we have the game state here, and we're going to take the piece, we're going to take its offset row, we're going to increase it by 1 because down is increasing row index goes downwards. Then we're going to check piece is valid. So remember that function, check piece is valid. We're passing in game piece. We're passing in the board, the width of the thing, and the height of the thing. If it's not valid, we're going to assume we collided. So we move the row back up, and then we want to merge piece into board. So we take the piece, so let's just send a game in there. Okay, so merge piece. So basically what the merge function should do is it should take the piece, and in the same manner that we translate the local coordinate system of the piece to the global one to compare it with the board to check for collisions, we want to do a similar thing, but this time we want to copy the values from the piece into the board. Okay, so let's loop. So first of all, let's get the Tetrino. Always need to get the Tetrino first. So the piece has a Tetrino index. All right, and then we want to loop through the cells of the Tetrino. And then we are going to fetch the value in that cell. Tetrino, we have the row and the column and the game piece rotation. Now, if it is a non-empty value, we're going to set the board matrix to that value. So we're passing that in, and we need to translate to the global board row coordinate system. So we have the game piece offset row plus row, game piece offset column plus column. So this is where we set things. So here we are, assuming that these are within bounds, because we're not going to call this function unless we're sure. So this function doesn't actually validate that everything's fine. It's just gonna do the merge. So that's basically all we have to do. So if it comes to this, we merge the piece into the board, and then we spawn a new piece. So for now, let's just do that. We're gonna implement that later. Actually, let's do one part of it. We want the offset column to be at the center. Okay, great. All right. Let's see. Update game. Okay. So when does the soft drop occur? So I usually like to use time-based dynamics, by which I mean that I use absolute time, or game relative time, to do the dynamics. So we're going to introduce a time field, which is the current time. Then we'll do a next drop time, so that in our game code here, we can check if time is greater than next drop time. You could do greater than or equal to. We'll do the soft drop. Actually, we can say while we'll do the soft drop. So if we skipped frames, we might drop several times. So this function has to determine what the next drop time is. So game next drop time is the current time plus get time to next drop. And let's see, the way that works in the Nintendo version of the game, which is what we're trying to replicate here, is that there's a number of frames that needs to pass depending on the level you're at. So this is based on frames, assuming that the game is running at 60 frames per second. So we're going to translate this into seconds so that we can work with time instead. So get time to next drop will be based on the current level. So let's introduce the level concept here. Level. And let's implement this. Get time to next drop given a level. What we're going to do is that we are going to create this array like this. Frames. What do we call it? What do we call it? We call it. We'll call it frames per drop. Actually, can we just be on and we're going to put those values in 48, 43. What else do we have? 38, 33, 28, 23, 18, 13, 8, 6, 10 through 3 5s, 3 4s, 3 3s, a bunch of 2s. How many? 7. How many was there? Yeah, 9. Okay, 1 2 3 4 5 6 7 8 9, and then 1. So this array should be 0, 28, 28. Maybe there needs to be one more there. Okay. We'll do this array, frames per drop, and then we'll compute the time to, where is it? Time to next drop will be frames per drop. Oh yeah, if level greater than 29, let's not go out of bounds, and then we divide that by expected. No, we multiply that by the target frames, seconds per frame. So target seconds per frame would be yeah, that makes sense. Where are we at? Times target seconds per frame. There we go. So we get the time to the next drop, and we set this next drop time, and when we're there we do the soft drop. If the piece is not valid, we merge it into the board and we spawn a new piece. So let's see if this actually works out of the box. So we're going to be at level 0. Why is it not dropping? Oh yeah, we didn't set game time. So let's do that. Here we need to get the current time. And then we just do game. Actually, let's do this. Game time is. Oh, sorry. Okay, we have a dropping piece. So let's see what happens when it reaches the bottom of the thing. So our window is 720 high. Our grid size is 30. Yeah, so it should be some room. Okay, seems to work. Let's try this one as well. So I can move into that piece and it stops there. Okay, it's looking pretty good, right? So let's also add a soft drop button. So let's do down. And that's going to be key state SDL scan code down, and D down will be input down minus previous input down. So that's the down button. And what we're going to do when the down button is pressed is force a soft drop, basically. So let's go to update gameplay. If yes, this one, yeah, let's do it here. If D down greater than 0, then we'll do a soft drop, essentially. That should do it. Yeah. So maybe we'd like to be able to hold the button and force it to go down, but let's try this instead. Yeah, might be a bit too quick. I'm not sure which one I prefer. Let's do this for now, and then let's also introduce the A button for a hard drop. So let's do input A, and let's bind that to the space for now. So DA is input A minus previous input A. Then we'll say update game. And then we'll say if input DA greater than 0. We just want to keep soft dropping until the piece reaches until the piece is fixated. So let's let this method return a value indicating whether or not we actually were able to perform the drop. So in this case we'll say false. So in this case we'll say true. So while we're soft dropping, just keep soft dropping until we hit the thing. There we go. Now we have our hard drops as well. It's starting to look pretty good. All right, let's do one more thing to make the board more visible. So when we're drawing the thing, drawing the board, we actually have a color for 0. Let's go ahead and let's go ahead and draw that to differentiate the part of the board from the general background of the window. There we go. All right, it's looking good. Okay, so now we need to start thinking about lines. So a line in Tetris is when a row is filled. When the row is filled, you want to remove that row and have all the rows above it move down one step. Then you get points and stuff like that. So the first thing we're going to want to do here is we want to be able to check if a row is filled. So actually, let's not do that, because usually in Tetris, when you get to line clears, a very nice gameplay feature is if the game pauses for a few milliseconds, let's say half a second, you pause the game, we highlight the lines, and then we clear them, and then the game resumes. So if we want to implement that feature, we need to be able to find which lines, which rows have currently been filled. So let's do a method called find lines. Let's find lines. And what we want to do here is that we want to go through the values of the matrix, and we want to see which rows are filled, and we want to report the indices of the rows which are filled. So as usual, we need the data of the matrix, we need the width of the thing, we need the height, and we're gonna return, or we're gonna fill an array of lines which we assume contains height number of elements, so that in each index position we can write a 0 or a 1, representing 0 meaning that the line is not filled, 1 that it's filled. And we also want to return the number of lines. So how do we do this? Okay, let's loop over the rows. And for each row, we want to check if it's filled. Check row filled. And that function will simply be we need the width, we need the row. So we're just gonna go over all of the columns, and if the cell is empty, we fail. Otherwise, if we go through all of the columns and none of them are empty, we have a filled row. So we check if it's filled, and then we go to lines out at that row and we set it to this, and then obviously we need to count here, and since filled is 0 or 1, we can just do this, so we don't need to branch, and then we return the count. Return the count. So this will find all of the lines. Then once we have the lines, later on when we actually want to clear them, we need to perform an operation where we essentially remove those lines that are filled and move every row on top of it down over it. And the way I'm going to do this is that I'm going to do it in line in the following manner. Let's see. Let's call the method clear lines. We're gonna get the values. We need the width. We need the height. I think we need this array of lines which we assume has height elements. Whoops. And what we're going to do is basically, conceptually, we're going to assume that we're creating a copy of the matrix where we have a cursor where we fetch rows from the source grid, which is the current state of the grid, and we have a cursor where we insert rows by copying them from the source. And basically we move, these cursors move together upwards. We start at the bottom, we move upwards, and as long as the row is not filled, we copy it. If the row is filled, we skip it until we find a non-empty row to copy into the destination. The destination cursor only moves if there's a copy. So as long as both rows are filled, we just copy. We reach the empty one. Okay, so this one, we copy this one in here. We go up here. We find an empty one. We skip that one. We find another empty one. We skip that one. We come here. We copy this one into there. This one into there. Then we no longer have any source rows left. So any remaining rows here will be empty. Make sense? So that's basically the algorithm we're going to implement. So this means we need two cursors. So we're going to have a source row, which is this one. And we start at the bottom, so we start at height -1. Then we are going to loop over all of the destination rows, also in reverse order, of course. Like so. And what we're going to do is, while the source row is greater than 0, which means that we haven't reached the top of the screen yet, and the lines array contains a non-zero value for that row, which means that the row is filled, we just keep we keep moving up the grid. If we exit this while loop and the source row is less than 0, we need to empty the row in the destination. So we do memset. The start of the row is at this address times the width. We set it to 0. We set width elements to 0. Otherwise, we want to copy the source row into the destination. So we do a memcpy instead, where this is the start of the insert. This is the start of the source, and we are copying width elements. And we move the cursor upwards. So that's basically it. Unless we've made a mistake, but it looks correct. I think we've nailed it. We'll see when we run the thing. So this is our clear lines method, or function. But we're not going to call this as soon as we have a filled line, because remember, we want to do the highlight thing. So let's start playing around with those game phases that we added early on. So let's go to game phase. So let's add a new game phase, which we'll call line. Basically represents the state of the game when we're highlighting a line. We want the game to pause. So we don't want to be running this logic, which we just implemented in update gameplay. We don't want to run this code when we're highlighting a line. Instead, we want to just suspend the thing. We want to draw the highlighted cells with some highlighting graphics, and then we want to wait until the highlight time period is over, and then we want to go back to the play phase. So essentially, update game line doesn't require input, and what we want to do here is, let's introduce a highlight end time, and it's just gonna say if time is greater than or equal to highlight end time, we want to clear the lines. Yeah, we need to know what the lines were, so let's put this one here. So we're going to store the lines that we're highlighting, the cleared ones, or the ones that are about to be cleared. So we want to pass the board in, the width, the height, and the lines. So we want to clear the lines, and then we want to set the phase of the game back to play. So in update game, if the current phase is line, we do this: update game line game break. Oh, sorry. There we go. Hard to type. Okay. So when do we go to this phase? Well, if we have filled lines or lines that need to be cleared, that's when we go to that state. And the place to determine that is obviously in the play update loop or update function. So let's create a on-stack array of lines. And let's do a, actually, do we need this? Could I just, let's just put it straight into the, let's do line count equals to find lines. We have the board, width, height, and we have the lines array, which we defined there, over there. Now, if line count greater than 0, then we switch the game phase to line, and we set the highlight end time to be the current game time plus, say, 500 milliseconds. Oh yeah, also here, we could compute our score here, or we could compute the score here. I guess we want to do it after the highlight has ended. I think it will look nicer if it just blocks, and then if you get the level switch afterwards. Yeah, so let's start with that. So we just changed the phase and we set the end time. So the next loop, we're not going to run this code, we're going to run this code instead. And this code is just going to wait for the highlights to end. We clear the lines, we go back to the play phase. But before we do that, we want to so I don't actually store the number of lines here. Maybe we should do that if we want to do it over there. So Let's call this one cleared lines. So we do this game cleared lines. Let's call it pending line count. That's better. It's more accurate. So here we can do line count. We increase the line count by the pending line count, and we want to get our points. So we have points, and points are based on a scoring system that looks like this on the Nintendo. So let's just do that. Inline is 32. Compute points, and it's dependent on the level and the number of lines you cleared. 1, 2, 3, or 4. So let's do level line count, and we'll do a switch on the line count. 1, 2, 3, or 4, and otherwise it's 0 points. And here we will return 40 times level plus 1. Here we'll return 100 times level plus 1. Here we return 300 times level plus 1. And if we have 4 rows, we return 1200 times level plus 1. So we're going to get some points here. Game points plus equal to the compute points, game level, and game pending line count. Also, we might progress to the next level, and that is based on this algorithm. So we need to check here if we should go to the next level. So let's create a function called get lines for next level, and this one needs to know what the start level was. And it needs to know what the current level is, probably. Yeah. Start level, yeah. Start level minus 50 lines. Okay, switch level. Play line clear start level times 10 plus 10, or the maximum of the number of lines, whatever comes first. Okay, we need to know the number of lines. Do we need to know the number of lines? No, we don't need to know the number of lines. So in the first level, you advance after one of these two conditions, and then afterwards it advances according to this rule for every 10 lines. So let's say first level up limit, it's going to be whichever comes first of these two. So we're gonna need a min method which says x less than y, x otherwise y, and we're gonna need a max method x greater than y, x otherwise y. So we need the min of either start level times 10 plus 10 or the maximum of 100 or start level times 10 minus 50. Bam, bam, bam. Now if level is start level, then we return this. Otherwise, starting from the level up level of the start level, for every 10 lines we need to level up. So the difference of the level from the start level, for each of these we need 10 additional lines. So it's the first level up plus the diff times 10. So here we need to then check if get lines for next level, game start level, game level. We need to know if the current number of lines exceeds what's required, is equal to exceeds what's required for the next level. And if so, we go to the next level. That's it. Oh yeah, we need to define, oh sorry, whoops. We need to define start level, start level. Okay, let's see what happens. Well, it worked. So it spawns the next piece and then it blocks. Let's see if we just increase this time a bit so that we can see that it actually blocks. Let's wait for an entire second. So fortunately we only have 3 limited number of, there we go, looks good. Yeah, this looks good. All right, let's also do the highlighting graphics. I actually want to wait with that, but let's just do that because it's, you know, you can get a feel for what it is I'm trying to achieve there. So render game. So if game phase, so we could split this one up into several functions as well, but let's just take an ugly shortcut and do it like this. If we're in this phase, we actually just wanna render a highlight over those rows. So what we're gonna do is we're gonna go through every row and if that row is among the lines, we're gonna do a rectangle there. Let's see. So it's going to be row times grid size x, y, width times grid size, and then just grid size and the height. And we're going to use some color here. Let's create a highlight color, which is gonna be white. That's our highlight color. There we go. We're just gonna fill that with a white color. Let's see if this works. There we go. Looks pretty good, right? There we go. All right. So let me just add escape as an exit key because I keep using that and it's not actually set. What's the scan code? Yeah, the key states here. Let's see if key states scan code escape. Is that the one? Escape. All right, good. All right, so let's put that pause down to 500 milliseconds because I think 1 second is way too long. 500 milliseconds. Let's also, maybe we should introduce the other Tetrinos now that, I mean, most of the gameplay elements are almost in place. We need some Tetrinos to actually mix things up here. So let's add the rest of them. Tetrino number 4 is going to be, let's do the S shape. That's it, right? No, that doesn't look right. I think it's supposed to be like this. Yeah, that's the one. And then the Z shape, which is just a reverse of that one. And then we have the this one. Oh, whoops. And then we have the final one, which would look like this. All right, let's get those in there. Tetrino number 4. It's a 3x3. Tetrino number 5, also 3x3. These are all basically 3x3 except for 2 of them. There we go. And then when we spawn the thing, spawn piece, we actually want to randomly select one. So let's do a random int in range is max minus min, return min plus random number divided by onto the range. That should do the trick, I believe. So that we can get random Tetrino here. Tetrino index. It's going to be between 0 and yeah, let's do this. Define array count of x is size of x divided by the size of x first element. All right. So, and the array count of tetrinos. Oh yeah, piece Tetris index. S32. Oh yeah, Tetrino index is a U8. Let's just do an ugly cast here because we know it's going to be safe. Alright, so now we should get random pieces. Yeah, look at that. We're getting all of the Tetrinos. So this is almost a playable game at this point, as you can see. Let's see if we can get a multi. We should get 2 rows now, and it works as expected. Very nice. All right, so we're almost done. We need endgame state, and we need a starting level selection. So let's just wrap up the final stuff, and we have a working Tetris game. So game over condition is something we want to check for in update game play. And the game over condition is that, so if you remembered, we had 2 rows that are outside of the visible range. So we don't want those. So basically, if we have cells that have been filled in that region of the board, that's a game over condition, right? So we have a game over row, which is going to be height minus active height, where the active height is actually, let's just do this. Game over row is 0. It's easier. If the 0th row has been filled, it's game over. So we want to say check row empty, right? Past the board, past the width, and the game over row. If the row is empty, if it's not empty, sorry, then it's game over. So we go into game phase game over. All right. So we need to implement this check row empty. So we have a check row filled. Let's also do a check row empty. Oh, sorry. Check row empty. We have the values, we have the width of the thing, and we have the row that we're checking. It's essentially the same as this function, except we do the reverse check. So if it's filled, we're not empty, otherwise we are empty. So we also need the game over game phase game over. There we go. And let's compile. Let's go to render game, and let's say else if game phase equal game phase game over. What do we want to do if the game is over? we want to draw the text game over on the screen. So we're going to have to pull some text rendering in, and I'm going to use STL for that again. So let's pull in TTF header, and we're actually going to need a font file for this, and I think I have one. Let's get, I think it's called Novem. Yeah, let's copy this into our build folder. I'm going to use that font, and we're going to use SDLTTF to load it. Let's go to our main function here. We need to initialize that first. If it fails to initialize, we return some code, and then the name of the thing is Novem how many underscores. So this is a public font. It's pretty nice. I'm gonna load that one using TTF open font. That's the name of the font. Size 16 is good. And then we obviously need to clean that up. Again, clean up. You know, if you're killing the process, if you're closing the process, you don't really have to do this, but let's do it. Close the font. So now that we have a font, we want to be able to render some text. So let's just go to our fill rec method. Let's do a draw text thing. Should we do that as a? So I think we want text alignment probably, because game over text needs to be centralized. Then maybe if you want to do like the score and stuff, it might not be centralized. So let's introduce text alignment. Let's just call it text align. So here we would do a draw string. We need the renderer. We need a font. We're obviously going to need the text. And then we do the usual offsets, where on the screen we want to render it, and the text alignment. And a color. All right, so first of all, let's convert our color to the STL color formats. So it's basically 121 GBA. Next. Yeah, so this is going to be super inefficient, but we don't really care, because this is just a Tetris game. It's going to work fine. So we're going to actually render text. It's going to create a what's it called? The render text solid. It's going to create a surface and then we're going to have to create a texture from that surface. We're going to render that. We're going to free that. So there's going to be a lot of allocations in the runtime. In the real scenario, we'd obviously never do this, but this is just a simple game. It's not going to, we're not going to have any performance issues because of this thing. So we're just going to do this simple thing and go ahead and do this. So this function will render the text. It will create a surface, so we'll know the width and the height of the text because it will compute that when creating this surface. So we can actually do the alignment. So we're going to create a rect, and depending on which alignment we want, text align left, text align center, we're gonna configure this rect, and then we're gonna do SDL. Oh yeah, we need to create a texture. Texture from the surface. We're gonna render copy basically means split this texture onto the screen. Now the texture, that's the rect. Then free the surface so that we don't mem leak, and destroy the texture. Destroy. Oh, leet speak was not intentional. All right, so if we are left aligned, it's simple. It's just the top right corner. The width is going to be the width of the surface. The height is going to be the height of the surface. So actually this one, we're always going to want to do that. So let's do that here. If we are centralized, we obviously need to move the x-coordinate to the left by half of the width. Y is the same. We're not aligning in the vertical axis. Let's just do that. And here we're gonna say we want to move all the way. We want to go to the left all the way for the entire width, so that it becomes right aligned at the point. That's it. So let's just try this. Let's see so that it works. So render game is going to have to get this font as well. So I'm actually going to pass that font in. And then let's try writing some text on the screen. Draw string. Tetris. Let's use highlight color. What did I miss? SDL font. It's called TTF font, right? Drawstring does not take 6 arguments. Okay, did I get that wrong? Drawstring. Render. Oh yeah. Alignment. Of course. We want it. Text align center. No, actually left for this test. All right. Let's see if we can get some text on the screen. Oh yeah. So let's copy that. There we go, x64. Let's copy all of the DLLs. Sorry about that. All right. Okay, it says Tetris in the corner. Very nice. I think 16 maybe was too small. Let's do a bigger font size because we're gonna. Yeah, that's better. Um, maybe even a bit bigger. Yeah, that looks very good. Okay, so um, if we're in the game over phase, let's just write game over, just big on the screen. Drawstring renderer font game over. We want to draw it dead center, so width divided by 2. Actually, yeah, we want the screen width and height. Or maybe not. I'm not sure. Yeah, let's do this first, and then we can determine. Let's do x equals width times grid size, actually, divided by 2. Y is height times grid size, because we need to, so multiplying by grid size transforms us from the matrix space to the screen space. That's where we want it. We want central alignment. Let's do the white color, it's fine. So we should be able to reach game over state like that. And once we reach the game over state, you know, there are no more pieces being spawned. You can't move, everything just pauses because the game's over. We're in the game over state. So what happens in the game over state is that if we press space, let's go to update game. Let's play, this is line. Let's add update game over. We want the input state. If space is pressed, we want to go to start state phase. So let's introduce that phase, which will be the initial phase of the game where we will select the starting level. So we press enter there, we go to, and if we are in the start phase, input state, input, and if we press A in this state, we go to the game. Go to play. Otherwise, we're just gonna do D up. So we can select the start level here, and then we start the game. And we actually need to set the game state here because we need to clear the playing field and make sure that, you know, we're in a clear state for starting a new game. And the way we do that is by clearing the board, spawning a new piece, yeah, that's about it. So um, should we do this? We can do it here. Board. Just clear that thing. We set the level to the start level. Line count to 0. What else? Points to 0. So usually when a game gets a bit bigger, I usually prefer to separate a session state from the overall game state so that you can easily just clear the game state, session state. But this is such a small game, I didn't want to do that, so we have to make sure we don't miss anything important here. And then the next drop time is going to be game time plus get time to next drop. So where's the error? Oh yeah. So now we start in the start phase. We press space. Oh yeah, I'd never added it to the switch. And that's the game over phase. Break is not a keyword, obviously. So, there we go. Let's see. Press space, the game starts. Okay, so we actually want to spawn a piece when we start the game because so that it has the appropriate status. Do we set the next drop time when we spawn a piece? No, we don't. So that's good. All right. Game over. Oh. It's not good. What's going on now? We're in some weird state. Let's see what's going on. So he's trying to get this Tetrino on the thing. It's going to spawn a new piece. Next drop. So it just keeps soft dropping. Oh yeah. We need to set the next drop when we spawn a piece. We need to do that. You know, I felt that that was the correct thing to do, and then we get a bug because we don't do that. So that was a good thing we caught that. So we actually want to do this when we spawn a piece. And it will also help us in the game start. We don't need to do that. We just spawn a piece, we get the next drop time. That's very good. One more thing, when we're rendering the game, if the game we only draw the piece if we are in play or line. Actually, only if we're in play. Perfect. Go. So that's game over. Um, mm, 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 mm. Let's write the yeah. So this it works decently. We don't have time to tweak that much further. So let's just draw the starting level thing when we're in that phase. Do we want to do that first, or do we want to do the sort of like current level and points thing first? I'm thinking maybe, yeah, maybe we want to, yeah, let's do like a small HUD thing first. So in order to do that, everything we're rendering here, we need to push that down a bit so that we have space to draw stuff on top. So let's just add a margin here. What would this look like? Yeah, so it got moved down. So what was the width of our window again? 720. Okay, so window is 720, grid size is 30. We got 20 visible rows, that's 600, so we got 120. Actually, we have 22 rows. Yeah. So we got 60. Okay, so if we do this, yeah, then the edge of the board is just at the edge of the window. Let's call it margin Y. Or it's actually padding Y. I don't want to rename it. Never mind. This gives us some space on the top of the screen where we can just write out, you know, the current number of lines. So if game, let's create a small buffer so that we can sprint some text into that. Let's use the safe mode. Size of buffer. Current level. Game level. And then draw string. Renderer. Font. Buffer. Let's do it in the top right corner. Yeah, let's pad it in, and left aligned. And let's just use the highlight color thing. We're just using that color. It's good. There we have the level, and then let's let's do the number of let's do our points. And then write the number of lines in the parentheses. Oh yeah, let's move this down. How was that? I think the font was 20 pixels high. Some more. 30. Okay. Okay, looks good. Let's see if it works. Come on, man. Give me a good piece. There we go. 4 lines, 1,200 points. All right, that's awesome. Now let's just all right. Now let's try this. I'm just going to increase the yeah. Let's hide the top 2 rows there, because those are not supposed to be visible. And let's just do an overdraw, because that's the easiest way. So we're going to render the whole thing, and then we're just going to draw over those. So we're going to start at height minus visible height in screen coordinates, and we're going to go the entire width of the thing. And we're gonna what's the height of the thing? 2 rows, obviously. Let's see, so I get this right. We got the margin Y, and we got 2 cells to cover. That's how it should go. And we're just gonna use black, I guess. I don't know. Let's try this. What's our fill rect method like? Render X, Y, width, height, color. There we go. Very good. Let's give this one some margin now that we have additional space. I mean, we could actually just write the number of, we could write the number of lines on a separate row, since we have more space there. So let's do that. plus an additional 30, so 65. It's going to be points. This one is going to be lines. So just a line count. There we go. Very nice. So we're not going to have time to do the next piece preview, even though that's pretty trivial to do. Maybe I'll do another video after this one to show you how to do the next piece preview, but we're not going to do that now. However, we will finish the start screen because we're doing a start level selection, which I just did. So we're starting at level 8, but we don't actually give any visual feedback to the user whilst that thing is happening, and that's not great. So obviously we wanna show that. So what I want to do is actually, I don't really like that game over state, so I'm thinking of doing it slightly differently. Let's do game phase. Let's do this. Actually, never mind. Let's keep that. If we are in the game phase start, we want to write some stuff on the screen. We want to write press start. Center of the screen. Actually, in order for this to be centralized, oh sorry, whoa, we need to add this Y margin, otherwise we're going to be off the center. We're going to write press start, and we are going, let's move this buffer. And we are going to present the starting level so that the user can see what it's currently set to. Starting level, start level, yeah. And we're just gonna render that underneath the press start thing. And we're gonna do x y plus 30. Can actually change the width of the window to match the size of the thing, so it's gonna be 300. Whoa, that's wrong because I did not check if it was greater than 0. I just checked if it wasn't 0. Same with this one. Greater than 0. Game over. Greater than 0. We don't want to trigger this on key release. We just want to trigger it if key is pressed. Let's go. All right, starting level 7. All right. All right. We have a working Tetris game with score and level progression and all that stuff. So let's just test this final thing that we just did. So game over, you press start, you can change the starting level and you can start a new game. You can keep playing for as long as you want to play. And when you don't want to play anymore, you exit the game, and that's it. So Tetris done. Now, obviously, there are a lot of things we can do to improve this game. I mean, we could do a shadow piece, which helps if you're gonna play with hard drops. Actually, let's do that. One final thing. Let's do that. So if we go to render game, if we are in play, we can do the following. If we create a copy of the piece and then we soft drop that thing, how did we, let's see, soft drop is on the game state. Okay, let's let's do it quickly. While check piece valid, piece game board. So we do this, we move it back, and then we draw it here, except I want to draw a silhouette. So draw, let's do a copy of this function. Actually, let's do this. Outline. So if it's the outline, we'll do something else. Let's pass outline, draw cell. So if we're just drawing the outline, instead of filling the rect, we just want to draw a rect. So we just want to do SDL render draw rect. Is that the name of the thing? Yeah, so we just want to do draw rect. So let's see, fill rect with draw rect. Let's just copy this. Draw rect SDL draw rectangle. So if we're doing the outline, we're just going to draw the rectangle instead of filling it. Then we return, and we'll use the base color. Do we use the base color? Yeah. Let's just do that. Using the base color. And then in render game, we're just gonna draw the piece, this one that we copied, and we're going to say outline true. What did I miss? Oh yeah, it needs to do all these calculations. So can it convert? Yeah, pointer to piece. All right. So now you see we have this ghost piece that tells us where it's going to fall if we hard drop it, which is obviously super useful. Yeah, it's a nice feature. I mean, it's a most of the modern Tetris games have this feature, so we have it too in our version, so that's very nice. All right, so that makes it for this video. It's already been a bit longer than I had planned, but hopefully I got to show you some cool features into this Tetris version. Even though we did a quick one, I think we still managed to get a lot of nice features in. I mean, graphically also, it looks pretty nice. I mean, obviously the layout of the textual information isn't that great, but I think the game overall looks pretty good. Yeah, I might do a follow-up video where we do additional features, or maybe go more in depth into how various parts of the game works. This will have to do it for now. So I hope you enjoyed the video, and I'll see you next time.